Working with binomial coefficients and the limitation of Pascal's triangle. As we explained in the previous lesson, Pascal's triangle is very helpful for determining the binomial coefficients when dealing with small degree binomials. For higher degree binomials, however, the use of Pascal's triangle becomes more complicated, as the triangle's base widens. For example, we cannot use Pascal's triangle to expand the binomial x plus y to the power of 317, as the base of Pascal's triangle would contain 317 plus 1 is equal to 318 terms, which would need a lot of space to write out and is therefore not practical. So it is necessary to use a more comprehensive method that is applicable in expressing the binomial coefficients of binomials of any degree. However, this method includes some concepts from combinatorics, an area of mathematics primarily concerned with counting, both as a mean and as a tool for obtaining results, and certain properties of finite structures. The first thing to do is to explain the meaning of these concepts before continuing with the general formula of the binomial coefficients. 1. The meaning of factorial. In mathematics, the factorial of a number is a particular function that multiplies that number by all natural numbers that are smaller than it. The symbol of factorial is the exclamation mark. For example, we have the following shown on screen. And so on. In general, we write for the factorial of any number n, we have the following shown on screen. Two special cases of factorial, 0 factorial, 0. Let's determine the value of 0. By using the following approach, we have the following shown on screen. Therefore, not only 1 equals 1 but also 0 equals 1. 3. The factorial of negative numbers. Following the procedure described earlier, we can write the following shown on screen. This division is impossible, as a number cannot divide by 0 because division by 0 is undefined. Therefore, negative numbers cannot be written in the factorial form. 4. The meaning of combinations. In mathematics, a combination is a concept used to describe the number of ways a group of elements extracted from a set of items can be combined with each other. More precisely, a combination is a way of selecting items from a collection, without repetition, where the order of selection does not matter. We denote a combination by C, N, K, where N is the total number of available items and K is the number of items per group. For example, C5, 3, indicates the number of possible 3 items groups formed by a set of 5 elements. Thus, if we have a set of 5 elements A, B, C, D and E, the number of 3-letter combinations is 10, A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A, D, E, B, C, D, B, C, E, B, D, E, C, D, E. The general formula used to find the number of possible k-elements combinations in a set of n elements, we have the following shown on screen. Note, we will prove this formula, and many other related things, when dealing with combinatorics as a separate chapter. We have n equals 5 and k equals 3, as the set contains 5 elements A, B, C, D and E, and we are interested to form groups of 3 elements each. Therefore, applying the combinations formula, we have the following shown on screen. After the substitution of the known values, we have the following shown on screen. Example. How many combinations are possible when forming groups of 4 balls out of a set of 9 balls? Solution. From theory, it is known that the number of elements in the set is denoted by n. In our example, n equals 9. On the other hand, the number of elements each group contains is denoted by k. Here, k equals 4. From the combinations formula, we have the following shown on screen. Substituting the known values, we obtain for the number of possible 4 balls groups formed by a set of 9 balls in the following shown on screen. We often express the n, k part not as a row but as a column instead. In this case, we no longer write the symbol C for combinations. In other words, the scripts are equivalent. We have the following shown on screen. This form is used to express the binomial coefficients theorem. We will discuss this at a later point in this tutorial. That is all for lesson 12.3.4. To continue this tutorial, please watch 12.3.5, the binomial coefficients theorem. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.